welcome. My name's Don DePaolo, and I'm the Associate Lab Director for Energy and Environment and the Earth Sciences Division Director. I'm going to get things started today, and because of the logistics, mainly because if we have the panels sit up here, they'll have the projector shining in their faces. We've arranged it so I'm going to say a few words of introduction, show a few slides, and then I'll introduce our illustrious panelists and our illustrious moderator, and then I'll turn it over to the moderator, Drew Isaacs, to take it from there. So this is the first in what we are planning as a regular series of both discussion sections or sessions and lectures on the Earth's carbon cycle, clean energy, environmental changes due to climate, and so on, all related to the issue of climate change due to energy production, and also what we can do about it here at Berkeley Lab from a scientific standpoint. This first edition, it will be a discussion, and so we have the three panelists, and we'll be each saying a few words about this first topic that comes up on the first slide, about what the Earth's future carbon cycle might look like. And then we'll open it up for questions, and we expect this to be both, fun, entertaining, and interesting to get to the questions as quickly as possible. Now, one of the things that we'll do, by the way, is we're redesigning the Carbon Cycle 2 website, and that website's going to have on it something called an Experts Corner, where the answers to frequently asked questions will be posted along with the experts who generated those answers. So we'll have people here taking notes, and some of the good questions that the panel is not quite prepared to answer accurately will be written down, and we'll try to get them the answers to those questions posted on the website sometime in the near future. So we welcome any and all questions. Okay. So in many ways, the discussion and the issues around the carbon cycle and energy sort of go back to this photograph, which was taken by an Apollo astronaut, which I think showed that the Earth is a finite object, that we're all involved in the effects that are, or in making effects or creating effects that will involve everyone, because we're all on the same planet together. It also shows one of the things that's critical for the future is the amount of ice on the planet. And ironically, it also shows the part of the world that's least responsible for climate change and its impacts, but is probably going to suffer as much as any other part of the world. Now, this slide, which we've produced also for the website, is adapted from one that comes from the Global Carbon Project and shows the rough estimates of fluxes of carbon that's going into the atmosphere and in various other places at the moment. So the big problem is fossil fuel combustion, which presently is estimated produces about 8.5 gigatons of carbon per year. This is not CO2, but carbon. And about 4 of those gigatons of carbon is accumulating in the atmosphere every year, and about 5 are taken up by, well, actually, there's another contribution from land use change, so that the total here is about 9. About 4 is going into the atmosphere, and then about 5 is being taken up by what is called natural processes, although the rates of uptake are not natural. So the ocean is calculated actually to be taking up about 2.3 gigatons of carbon per year, and then what's left in order to balance the fluxes is the land sink, and this is the terrestrial biosphere, which in some way or another is taking up 2.7 gigatons of carbon per year, and that's probably being transferred into soils. So this is the situation that we're faced with at the moment, and the big problem is as the atmosphere continues to gain CO2, the greenhouse effects will increase. Now, if you go back to the natural carbon cycle, the big difference between the current carbon cycle and natural carbon cycle is that the typical transfer rate of carbon from deep geological reservoirs into the atmosphere which takes place mostly by volcanism, but also by leakage through the crust and other places, is about, this is probably on the low end here, but it's about 1/10 of a gigaton of carbon per year. Now, some people have pushed this number up to 0.2, but it's a lot lower than 9, and it's nowhere near 9. Okay, it's close to 0 in comparison to 9. So the normal system is used to moving carbon around, but it's used to moving carbon between reservoirs in terms of a net flux at scales of about 1/10 of a gigaton carbon per year. Now, if we were to go into the future and imagine that we can produce enough energy for us to have a lifestyle that we would like to have, and also not have an increasing carbon concentration in the atmosphere, it would look something like this picture here, where we were using solar PV, energy efficiency, artificial photosynthesis, being more efficient at using carbon, and also capturing carbon and storing it somewhere geologically that's not in the atmosphere. So the big challenge is that at the moment we produce a certain amount of energy and we're giving off a lot of carbon. This comes out to a number like 60 megatons of carbon for every petawatt hour of electrical energy, or electrical energy equivalent. And what we might need in 100 years would be 2 or 3 times that amount of power, but with 1/3 or less of the amount of emissions. And so this number becomes lower by almost a factor of 10. That's the challenge. Now, one confusing aspect of the carbon cycle is that the near-surface parts of the Earth exchange a lot of carbon every year. The atmosphere, the terrestrial biosphere, terrestrial soils, and the surface part of the ocean all exchange carbon very rapidly with one another. And these numbers are in terms of gigatons of carbon per year, and they're rough numbers. And what you can see is those numbers are very large. But this is like, you know, all of us here breathing in the room, we're taking CO2 in, oxygen in, CO2 is coming out, there's some airflow coming through the room. You know, we all breathe every year, and a lot of CO2 and oxygen go in and out, but in the end, it doesn't change the atmospheric concentration of CO2. Much in the same way, carbon gets shifted between these reservoirs every year, but it doesn't change the total amount. If you draw a box around all of these reservoirs, there's about 3,700 gigatons carbon in there, and not much goes in or out of that reservoir every year. What does go in and out is what comes out of volcanoes and what eventually gets transported to the deep ocean and precipitated out. So don't get confused by these, is the issue. There's also a deep carbon cycle that completes this. So the point is that up until now, we've added about 500 gigatons of carbon to the system. And it's been distributed between the atmosphere, the surface ocean, the terrestrial biosphere. By 2200 AD, depending on whether we do well or not so well with regulating the amount of carbon we produce, we could put either another 1,000 gigatons of carbon in, or even as much as 4,000 gigatons carbon. So what we would be talking about on the high end is more than doubling the total amount of carbon in these reservoirs. And the question is, where will it go? And if you look at the present distribution, it's about 45% to the atmosphere, 25% to the ocean, and about 30% into terrestrial soils. But what we don't know is whether those proportions are going to stay the same. But in any case, even if they stayed the same, a lot of additional carbon will go into the atmosphere. The atmosphere is now up to about 800 gigatons. But if half of 1,000 goes in there, it'll go up to 13. And if half of 4,000 goes in there, it'll go up to 2,800. So this is an important thing to keep in mind. So basically what we're doing is just pumping carbon into this surface reservoir. And if you were to compare the fluxes from burning fossil fuels to the fluxes that are typical of the background, this is what the width of the arrows would look like. So although you can argue about whether the temperature is going up, you can't argue about whether we've disturbed the carbon cycle. Okay. Now, this last point of whether or not the terrestrial system will continue to benefit us in the same way it has up until now is shown on this diagram, which shows a bunch of model curves, which the negative numbers here are the amount of CO2, actually carbon, per year taken up by either the terrestrial biosphere or the oceans as a function of time between 1850 and 2010. And where we are now has the ocean taking up about 2.5 gigatons of carbon, has the terrestrial biosphere taking up a similar amount. And what you'll see is that the projections by the models, from the models for the future for the oceans are all about the same, and it continues to increase. So the ocean continues to do its job for the next 100 years, but there's a lot of uncertainty about what the terrestrial biosphere is going to do. And actually, if you take this out another 100 years, which would be appropriate, you would see that those uncertainties would widen out still. So the uncertainty in the amount of CO2 that the terrestrial biosphere is going to take up is roughly equivalent to the amount that we expect to save over the next 100 years by increased efficiency and lower carbon energy production. Okay, so ultimately we're here because the lab has an initiative called Carbon Cycle 2.0, which is about garnering our capabilities to make an impact in this overall issue, both in the way we use carbon, alternative ways of making energy, and ways of understanding what solutions we may propose are most likely to be effective, and in understanding what the climate consequences are going to be of any choices that we make, including not changing to do anything. The developing world, of course, is a key component of what's going to happen in the future. That's the part of the world that wants its standard of living to be increased. There's a very large number of those people, and that's going to increase the energy demand. At the same time, we're trying to keep the carbon emissions down. Okay, so I'm going to stop there. I'm going to ask that the projector be turned off so that the panel can come up on stage. And let me just say a few words about our panelists. So I'm going to be one of the panelists, and I've already told you who I am. Ashok Gadgil is on the far side of the table. He's the director of the Environmental Energy Technologies Division. He has a PhD in physics from UC Berkeley. He's gotten many awards and done many important things with regard to environmental engineering, really. And he's patented something called UV Waterworks, which is a technology to inexpensively purify drinking water in developing countries. He's gotten many awards, for instance, the Pew Fellowship in Conservation and Environment. Paul Alivisatos, you all know, he's the director of the laboratory. He has a PhD from UC Berkeley, and he's been here on the faculty since 1988. And of course, his field is nanomaterials and nanotechnology, and he is maybe the world's leading expert in that area. Our moderator today is Drew Isaacs. Drew is from the Haas School of Business. He's an adjunct professor, and he's a director of a number of programs and centers, and they all have very interesting names. He's a director of New Management of Technology programs. He's also the co-executive director of the Center for Energy and Environmental Innovation. He's also director of a program called Bridging the Divide program on technology in the developing world. However, most interestingly, he has both a bachelor's degree and a master's degree in geochemistry from the University of Michigan. So, Drew, it's now yours.
Thank you, Don. Well, it's a pleasure to be moderating this event today. I like to say to my MBA students that you are what you worry about. So worry about something big. And all I can say to our panel is, you sure have picked a doozy. I was hoping that Don, in his introductory remarks, would actually give us some solutions instead of just laying out the problem. Thank you, Don, for casting the current situation so well. But it also perfectly sets up the discussion that we're going to have today on this fundamental and fundamentally important subject regarding the carbon cycle. I'd like to ask each of the panelists to pick up the conversation that Don has teed up for us so beautifully. We'll hear first from Ashok, and then from Paul, and then from Don himself, if you'll take your comments a little bit further. Then I'll ask one or two questions of the panel, and then we'll open it up for discussion among the group. And so I'm going to ask what I always ask of my classes, which is start thinking now about what questions you'd like to ask the group. This session will go very quickly, and if you have a question, if you should have a question on a topic this big, then please jot it down as we go along, and hopefully we'll be able to capture everybody's questions and everybody's input. So let's begin. Ashok, would you like to take it from here?
I think Don pointed out correctly early on that we are planning to go, we need to go from 140 petawatt hours per year of power production now to about 400 petawatt hours per year power production by end of this century. I'm thinking of a long-term vision, as I'm supposed to look to, of what would be Earth's future carbon cycle, where we will be back in equilibrium. People who pay the first cost are not the people who pay the energy bills. So there are issues about what are the societal drivers to actually realize on scale currently known technologies that will actually be implemented, not simply the question of doing invention. So that's the first point. Second point, we badly and seriously need to invest in invention. Invention is the seed. While societal drivers might be thought of as water and soil and sunlight, if there is no seed, all amount of water and sunlight is not going to do us much good. So invention is critically important, but it's not the only solution. It's necessary but not sufficient. Lastly, I think indefinite growth in population and indefinite growth in material throughput doesn't sit well with my vision of how we are going to come back in equilibrium regarding the Earth's carbon cycle. It's not a mathematically provable theorem. It's more of a judgment call if it sits well or not. But my sense is we got to manage both if we are going to get back into equilibrium.
Thank you. Paul?
Okay. Well, thanks, Drew. And, you know, one of the great difficulties that we will encounter in this panel is Drew said at the beginning, think about what your vision of the future carbon cycle would look like. And, okay, we tried a little bit to do some of that by laying out, if you look at the diagram that, recall the diagram Don had put up a little while ago of the carbon cycle initiative at the laboratory, you'll see we have on there certain things. For example, we have how we use. So there's combustion. We would like to burn it more efficiently if we possibly could, to put as little carbon as possible into the atmosphere when we get usable energy from it. There's capture and sequestration, which almost certainly we're going to need to do because we can't really stop using carbon very quickly. May eventually. We've got biofuels on there. Clearly that's a complete cycle. If we're using biofuels, that would be terrific, but the power efficiency may not be good enough, so then we have artificial photosynthesis, which of course could be a long-term, stable solution if it was much more power efficient than biofuels. So that's kind of, that arc kind of looks at how we use carbon, and then the rest of the diagram shows the, the off-ramps for efficiency, for helping the developing world to have, more technologies which are low carbon but appropriate to their needs, and energy storage and photovoltaics. And of course, in the center of the whole thing sits our climate modeling and energy analysis. So there's a structure to that diagram. You say, well, what do the carbon cycle looks like? Well, to zeroth order, that's our guess. Okay, and I think that's an appropriate guess. And if you look around that, and I would urge anyone here at the laboratory that's interested in this topic to start to think about that whole carbon cycle and to think about whatever research you do, how is it going to fit into that whole thing sometime in the future. And so, that's a vision, of course, for, pieces that could lead us towards what a future carbon cycle might look like. But the thing I have to say, to be honest about it, is that what the laboratory really needs to be focusing on, of course, is to provide underlying science that can help our whole system have options in the future for how it can deal with this problem. And one of the difficulties that we face is that if you talk to people who are in the field of economics or policy, they'll pretty much uniformly say, well, this is a problem that can be solved. What would the future of the carbon cycle look like? Nobody needs to try to guess it. What we should do is have a price on carbon. And very quickly, a lot of innovation will occur in response to that price on carbon, and nobody's going to anticipate all the features of what that future carbon cycle will look like, but it's going to be one which will plausibly accommodate that price on carbon in such a way as to realize a more stable carbon cycle. So, in a sense, it's a kind of a dangerous question to answer too much, because in truth, it's such a big problem. Nobody can completely know the answer to that. On the other hand, it is, to some degree, our duty to kind of try to sit here and think about what is the future going to hold in this area, and to try to lay out research initiatives which we think map onto the largest components of that, while being mindful of the fact that there could be a scientist here in this room someplace that's going to come up with an innovation that will completely upend what our thinking is. Hesitantly also partly because energy is such a slow thing to change. Many people will say, well, if it hasn't been invented already, it's not going to be part of the solution in the near term. And I hear that, and there's some element of truth to it. But on the other hand, that's why we've laid out the pieces that we have that are on that diagram. So, those are some of my thoughts about the future carbon cycle. We've tried to guess to the best of our ability what the big things are that we ought to be working on as a laboratory, which are the things that you see kind of as circles in that Carbon Cycle 2 initiative. But we have to do that somewhat humbly, and accepting that, if an innovation system was unleashed, it would go in unpredictable directions. So we have to be nimble to kind of respond to what those changes will be.
Okay, thank you. Well, I agree with what has been said so far, but let me say something a little bit more specific. I'll preface it by mentioning something that Steve Koonin, who's the Undersecretary for Science, said in a talk that I heard just yesterday in D.C., where he gave the example of New York City in 1850 and the problem of horse manure. You've probably heard this analogy before, that when they projected the growth in personal incomes over the in the future in New York City, and the fact that everybody who didn't have a horse at that time was going to want a horse, they projected that by around 1900 or 1920, the city would be about 3 meters deep in horse manure. And then if things didn't get better and people got even richer, that was going to be much deeper than that by 1950. So I'm going to tell you, my view of the future is that we're going to be stuck in the horse manure stage for a while. And the horse manure analogy is coal and natural gas. We'll spend, and oil as well. So my view is we're going to be burning a lot of carbon, and the big issues are where that carbon's going to go. And the half of the issue is the one that I mentioned with regard to the terrestrial biosphere. If we can cajole it into taking up a fair amount of that carbon, that would be really nice. If it turns its back on us and stops taking it up, it's not going to be nice. One way or the other, we're probably going to have to sequester some carbon. So what we're working on mainly now is to capture it from coal-fired and gas-fired power plants. And even if you could use biomass to burn, which means you took the carbon out of the atmosphere to make the biomass, then you burn it, capture that carbon and sequester it, then you can actually go negative. In addition, if things get out of hand and the CO2 concentration in the atmosphere clearly is way too high and we can't stand it because of the climatic effects, people are working now, and maybe they'll perfect ways of economically taking CO2 out of the air, but still you're going to have a place to put it. So I think there's going to be a lot of carbon sequestration being done in the next 200 years. And the carbon's probably, hopefully, going to go into the terrestrial biosphere in some kind of quasi-natural way. But secondly, it's going to be pumped underground in continents, and we're probably going to be pumping into the deep ocean as well, because that's a very big reservoir that could stand to have probably tolerate having another 1,000 or so gigatons of carbon.
Don, I haven't been in New York in a while. Did they ever solve that problem?
Only literally.
I wanted. I'd like to ask each of you to drill down a little bit into what you said for the following reason. Ashok talked about energy efficiency and also the issues associated with indefinite growth and what comes from that. Paul talked about also about efficiency related to combustion, biofuels, and other things. Much of it related to fuels and the use of petroleum hydrocarbons. And Don introduced or took the discussion regarding carbon capture and storage a little further, and also talked about large scale. I think it's called geoengineering these days. Large scale solutions. But all of these have kinetics issues associated with them. And so I'm wondering if I could ask each of you to talk a little bit about what solutions seem appropriate for the short term, for the medium term, and the long term. And since those are undefined periods of time, I'll add a little bit more in the way of boundary conditions. Short term, let's say on the order of a decade or two. Medium term on the order of perhaps half a century. And long term, I suppose, longer than that. Ashok, could you talk a little bit about what you see as solutions in those 3 different time frames?
Sure enough. I think in the short run, a decadal time scale, single decade. I probably don't need this. I think I figured out how to make my mic work, right? Good. So on the time scale of 10 years, we are already ready to pull the trigger on very aggressive energy efficiency implementation, both in the industrial countries and in the developing countries. But as Paul alluded to, the question is, are the policies in place to create the business environment and the markets to make the technology go out to scale? And that is a larger policy question. That's also a political question, not simply an invention question. But in the very near term, I mentioned buildings, and buildings are important because in the US or most industrial countries, buildings take up 40% of energy. Buildings take up 70% of electricity in the United States. So cutting that back by half, if you knew how to do it right, would be terrific. But that's only for new building. But we need the policies and the societal push to take technologies and inventions that are known to implementation. And some of that has already happened. In the medium term, I think what seems to be closest to maturity are technologies which are ready to go to scale, but which have bottlenecks like wind power, where the grid is the bottleneck now, not the wind machines, but building out the grid to reach the places where there's a lot of wind, but where we don't have much use of the electricity. So you need to figure out how to invest in massive grid extension to regions which are not densely populated, very windy, to feed the wind back into the grid where the populations are. And that's the scale of just a handful of decades where we can build that out, maybe even faster. Longer term are critically important things where we actually go to zero carbon sources and where we test, mature, and implement massive sequestration of CO2. So that's the kind of time scale I envision. But as Paul said, there could be people here who would completely surprise us in a good way.
Well, am I on? Yeah? Okay. So let's imagine, if you're saying within 10 years, within 10 years, of course, in the energy industry is just, a blink of an eye, right? It takes so long to build infrastructure and to implement energy technologies. Many of you might have seen, in some of our presentations, we have a little graphic that shows, the 30 gigatons of CO2 that are emitted every year, 9 gigatons of carbon. So you take that 30 gigatons that's being emitted and compare that to the top 100 chemicals produced in the world, bulk commodity chemicals, that's about half a gigaton. So, the total amount of CO2 emitted is 60 times larger than the top 100 chemicals produced globally. So you get a sense of it. It's a very, very big industry. So 10 years is a blink of an eye. So for anything to happen inside 10 years, it has to exist already. That's the bottom line. It's just nothing can really be implemented on a very large scale that sort of doesn't already exist. So what could be done in the short term? Well, one thing would be a shift from, for us in the United States and many parts of the world, a shift from coal to methane, to natural gas. Many of you will have followed that in the last several years there have been discoveries or technical developments of how to, through fracking and other things, to extract much more natural gas than had previously been expected. It's led to a situation where the supply of natural gas has increased dramatically. The cost of gas is way, way down. In fact, it's still the case today, and I don't understand, Drew, somebody from the business school or the economics department is going to have to explain to me how it's possible for a few years to have gone by, and still there are natural gas plants which were built originally as peaking plants, that are there to kind of, as problems emerge on the grid, to be able to kind of quickly come online and offline. There's still a lot of capacity of these natural gas plants that have not been shifted over to baseload, even though the price of natural gas has gone down enormously. It's clear I don't understand completely energy economics, because if a utility company was getting its energy that way right now, it would be far more economical. So there's lots of social and economic factors that come into this. But the fact is, if you shift it over from coal to natural gas, right away that would have an immediate impact, because the amount of carbon emitted per usable unit of energy is so much less. And that could be done on a large scale. And that could be done pretty quickly. And then in that next 10-year period, we actually could be implementing parts of the capture strategy. So, and if you look at that, just to give you some qualitative numbers there, the capture, if you want to capture the carbon from a source like a natural gas plant, it would probably cost in the neighborhood of 8 cents a kilowatt hour. You probably pay in about 12 cents, and that, if you're a typical consumer with the incomes of many people at the laboratory, you start at 12 cents coming from PG&E, but you go up to maybe 40 if you're an energy hog. So they have a graded price here, but it's in that range. So the extra 8 cents. I mean, I don't mean by any means to say that it's insignificant, but it's not something that would completely change life as you know it. So it's something that could be implemented. So in that we could implement capture at a pretty large scale, perhaps 10 years from now. And that would be quite viable. At the same time, within this decade, these 10 years, we could be putting in place efforts to substantially expand our renewables base. As you probably know, the solar area has had remarkable developments, with the prices dropping really very, very significantly in the last few years, for a variety of reasons, but a lot of them having to do with improved manufacturing. So the prices of solar have come down very, very dramatically. Of course, wind is already really competitive in many ways. And as Ashok pointed out, some of the limits are just not having enough grid. If we had the right policies in place, we could, within a decade, start to see substantial ramp up of the fraction of renewables that are there. For a long time, the scenarios that I was seeing people talking about said that maybe 20 years from now, we might be looking at a scenario where we would have a third still combustion with capture attached to it, a third of the energy coming from renewables, and a third from nuclear. It's a possible scenario. There's other scenarios. You could go to a very heavy carbon and renewables one with a much lower fraction of nuclear, or vice versa. But you could implement those kinds of things on this sort of 20-year time frame, and you could see those things, you could imagine implementing those things on that kind of time scale. And the technologies many of them are in place for that, not all of them. We're missing things. For example, the transportation sector is the last thing I'll say. The transportation sector right now can really only be fed by fossil fuel. The only way we can run automobiles and trucks and things like that is by burning a fossil fuel right now. So that's why the electric vehicle is so important. That's why battery research is so important, because if we had electric vehicle, then any input source that we ended up choosing 15 or 20 years from now, be it nuclear or renewables or methane or anything, all of those could drive the transportation sector. So electric vehicle kind of sits there as a real fulcrum point that's undecided. Are we going to be able to implement the electric vehicle on a large scale? The battery technology doesn't look like it's quite up for it yet. And so, you know, that's a place where research really could make a very dramatic difference in the next few years. And the scenario that you will end up implementing in terms of the balance would not be affected if you could get the electric vehicle part to work well. So that's why it's so important. So that gives you kind of at least a thumbnail sketch. Yeah.
No, you want to comment on time frames?
Sure. I'll keep it a little bit shorter. Just going back to carbon sequestration and the numbers that Paul quoted of increasing the price of electricity by about 70%. That number is a useful one to think about, because that assumes that you instantaneously add carbon capture and storage to all existing power plants. But I think the issue for the short term is to get started. If we were to equip, say, 2% of the power generating capacity each year, we would only be adding in 2% of that 70% increase each year. And if this was done at the federal level, so that there was a policy to spread that pain around, rather than just at the specific sources where they were being retrofitted, I think we could start ramping up now. And the point being that we need to already be there in 30 or 40 years. And if we can start now with policies that will encourage retrofitting of old power plants, and also building some new power plants to replace the old ones with incentives, I think that we can get to a pretty good place. If you combine that with the efficiencies that can be gained by, you know, just existing technology on automobiles and buildings, I think we'd be taking a big chunk out of what we need to do in the short term.
We're going to open it up for questions in just a minute. I'm going to ask the panelists one more short question. I hope that you've jotted down some questions you'd like to ask, too. Here we go. There's a sort of an axiom in economics that if things are inexpensive or free, people tend to use a lot of them. And that, it seems to many people, is one of the core challenges that we have in looking at issues related to the carbon cycle. At whether electricity is 9 cents or 19 or 29 or even 39 cents a kilowatt hour, that's pretty inexpensive for the service that's being provided. And even at the current gasoline prices in California at $4 to $4.50 a gallon, it's still quite inexpensive. And actually, some students just a couple weeks ago worked up that that of the 5 costs associated with operating an automobile, 4 of them are more expensive than fuel, which is actually the least expensive attribute associated with operating an automobile. The more expensive ones are things, the depreciation of the vehicle is twice that of the fuel use, even at these elevated costs, and other costs associated with insurance, risk, health, and so on. So we have an issue where energy in the current environment, in spite of what we see in the newspapers daily, energy is, well, inexpensive. And the proof of that is the fact that people use it pretty much, people's behavior certainly is consistent with inexpensive energy. I'd like to ask the panelists to spend just a minute talking about the challenges that exist for our laboratory in driving forward both research and also guiding the public discourse in an environment where people think energy is expensive, but yet the behaviors indicate it's inexpensive, and trying to change the carbon cycle as a result. Paul, maybe we'll start with you.
Gee, thanks. That's a question, Andrew. Well, you know, on this issue of expensive and inexpensive, it's a tricky business there. I mean, I would say that, for instance, of course, perhaps we could find, to this point, for example, of this 8 cents a kilowatt hour for the carbon capture cost. That's, of course, assuming today's technology. And interestingly, today's technology in that case, in the carbon capture case, is off by about a factor of 10 from where a thermodynamic limit is. And so it may very well be possible to bring that cost down by a factor of 3. So let's say that you did. Let's say you got it down to 3 cents a kilowatt hour or something like that. Well, at that point, the solution has become inexpensive enough that actually it just gets implemented, and that's the end of it. You know, it's not something that's so painful anymore. So you do have to factor that in, that the technology can come into play in such a way that you know, I mean, implicit in your question is what should be the price on energy if we want to really modulate behavior. And I guess I'm saying that also depends a little bit on the technology and how it develops. And there may be some solutions which don't require a massive increase in energy costs, which people really don't want to have happen, and which I don't really think in the end is necessary. Perhaps yet another way of saying this is, if you imagine the technology solutions that could make a stable carbon cycle with just today's technology, just brute force, say, let's just say, take today's technology and we're just going to, you know, try to have a completely stable carbon cycle. What's the total cost of that? It turns out that the numbers are not so outrageous. Okay, they're not enormous numbers, and you know, this 8 cents a kilowatt hour kind of gives you a feeling for what they come out to roughly. So my sense is that although it is true that energy is cheap, it's not necessarily true that it has to be incredibly expensive in order for us to bring this problem into control. That's my opinion on it. And the fact that energy is cheap then has a lot of positive benefits because it enables lots of other economic activity to take place without having huge constraints on it. So to the extent that that's a viable thing for us to do, then you know, that's something I personally kind of would like to see, you know, see us evolve towards a direction in that way, and not towards one where we had to have a massive increase in energy prices. And I will say that also I think in the interim, if we did apply even a relatively modest, really quite modest price on carbon, as long as there was a price on it, just a price on it, non-zero price on carbon, it would drive massive changes quickly because the system is so far out of where it needs to be in that space that even that modest cost would already start to have effects that would be quite noticeable. So that's my opinion on that one. Yeah.
Well, I guess related to Paul, I might look like a pessimist. I might look like a pessimist in the sense that I think it's really important to certainly. I mean, I agree with the last point you made, Paul, that a price on carbon is critically important in one way or the other, whether you call it a carbon tax or you call it tradable carbon permits or do some direct or indirect way to do this, emissions permits. The key point in every case being that there is at least an agreement in principle that pulling carbon out of the soil or out of the ground and burning it and throwing it out into the air indefinitely is not the right way to go. It's going to be always difficult to compete with pulling carbon out of the ground, burning it as your source of energy and letting the CO2 go into the air, and you want to compete against that with capturing energy from the sun. That's a pretty high bar, and having a little bit of cost to polluting the limited capacity of the atmosphere or taking up the capacity of the atmosphere is certainly worthwhile to try to level the playing field here for carbon-free sources of energy. So I'm all in favor of that. And I think societally there's got to be somewhere a recognition that things that cannot go on indefinitely have got to stop. And if we don't stop them voluntarily through policy and political means, they stop anyways, but with much more unpleasant consequences for everybody around.
I'm going to answer this with some kind of twisted philosophy that it's more philosophical than the others have been. In my view, it's an issue of what drives our behavior. And it's a question in my mind of, well, the way I like to think about it is the standpoint that one would have to have in order to behave differently is one of what I call planetary stewardship. It's been clear for decades now that we basically run the planet. We can affect the natural systems greatly enough that we have an option now to figure out how to run them well so that they'll serve us in the long run and sustainably. But this is not what drives behavior for the most part. And then when you think about climate change and the impacts are going to be most serious for people who aren't born yet and don't live in this country. And then the question of morality and what our responsibility, our ethics, and morality are to people who are not yet born that might live 200 or 300 years from now. And actually, if you look at some of the projections, if we're not very good at limiting carbon, 1,000 years from now, do we have any responsibility to those people? So the question really is, how do we think about ourselves on the Earth? I think if it's all, in the end, it's going to be economics in the short term, but I don't know how we will switch to that, to a different view of how we interact with the Earth. And just, I'll leave you with this anecdote. In the year 2000, in June, May, I was asked to give the graduation address for the Earth and Planetary Sciences Department on campus. And so I finished up my talk with this idea of planetary stewardship. And you remember, this was, toward the end of the Clinton administration. And it was only, it seemed like it was ripe. And the thing to tell the graduating students was they were going to be responsible for this issue of planetary stewardship. And then George Bush was elected in November, and everything was put on hold for 8 years. And we sort of forgot about that altogether.
We're going to go ahead and open it up for questions.
Bruce King. We have a population that has a very rudimentary understanding of climate change, is not willing to change very fast. They vote for politicians, and the politicians are afraid to use the word climate change. At best, they'll use the word clean energy. And the politicians are responsible for setting our policy, and we've got politicians that are ready to tell EPA they can't regulate carbon. So it seems to me we have and that's just in the United States where we have a pretty good understanding of this. How do we change policy if the politicians and population aren't willing to change? It seems to me we have to do massive marketing.
I had a great, I'll just jump in on that. In the last 3 months, I've spent a lot of time in Washington, D.C. And one of the things that I've had the opportunity of doing actually has been to meet a lot of the newly elected freshmen in the Congress, in the House. And you're right, they're not particularly strong supporters of climate change science. So there's no question about that. I'd like to relay to you a very interesting conversation that I had with Congressman Nunnally, who's newly elected in Mississippi. And it turned out, before going to see one of these folks, and he's on the Energy and Water Committee, so he has some influence over the future of this laboratory. And, before going to talk to these folks, we do some homework. And so it turned out that, Steve Salkowitz and colleagues in Ashok's division have done all this great Windows research all over the years. There's this company, Solidyne, that's a terrific company that makes window coatings that can save energy because they reflect infrared. And Solidyne is making a factory in the congressman's district with 350 employees. He was very happy to see me. He was very happy. And we had a great discussion. And he said to me, it turns out that when he was a young person in elementary school, he was growing up during the era of the space race. race to the moon. And he would build little models of all the spacecraft and stuff, and it was so thrilling to him to be involved. This is what he just volunteered. I was sitting there listening, it was amazing. So he built all these things, and it was very exciting for him. And that ultimately, he never would have understood until he had grown up later how all those investments in NASA had turned out to generate all kinds of new technologies that had been unanticipated, and that he thought that the nation, and this is a new freshman Republican congressman, they thought that the nation needed to have some challenges that brought forth the best in people for common good in that nature, in that type of thing, and that he himself supported very much that we would set a 10-year target for having complete energy independence in 10 years. So to my mind, there's many ways of talking about this problem, and the climate change problem is one. There's energy independence. To my mind, it's something I'm not enamored of that concept, because in fact there's this one atmosphere, and so whatever happens here and there, they're all connected. You can't really disconnect them, but you can understand the motivation behind the comment. And also very much the palpable sense that there's such an opportunity to seize what is the largest industry in the world, the future of that industry, that there is a basis there for a discussion around what could be future technologies, what could be future industries, and ways in which we could do things for, there's a basis for that discussion that could allow us to get to a lot of the places that we want to go to in a way that's productive. So, it's not as bad as you might think.
Other questions?
Hi, Bill Scholander, and this may be harping on the same type of theme here, but it seems like a lot of the connection of the science. I'm actually impressed that there's as many good solutions as there are, and that there could be if we just were willing to do it. But it does seem like we need to connect into the needs of society and make it communicate it that it is a viable solution and it's not that expensive, and yet we're realizing the costs of those in indirect ways, the externalities. So is it time for science to get a publicist?
This is a perennial question, isn't it? Is it time for science to get a publicist?
I'll just make one comment. Well, the answer, I think, is yes. It's just a question of what the definition of a publicist is. In some way, the message that we wish to send isn't clear enough to a large enough part of the population and isn't being delivered widely enough. So there's something that we need to learn that we haven't learned yet. And part of it may have to do with the way information is now transferred, in small bites and quickly, and with a certain kind of innuendo that goes with it. And we might need to learn to do that better, because only a certain fraction of people are going to be probably educated to the level that they can fully understand all the issues and certainly the technical aspects of the problem. But we could get the message across. Of course, starting up a few additional 24-hour news television programs probably wouldn't hurt either.
This is a little bit to the earlier comment that you may have a better vehicle for the message packaged as energy independence, which itself is hard to define, but it's hard to be against energy independence. Whereas it's it's a relatively easy thing to grasp without drilling into it too deeply. Whereas it's very hard to fully get our heads around some other things that might look like they're far in the future and deeply dependent on other. But I think this is to your point about messaging is pretty darn important. Other questions?
Trent Northern, thinking about planetary stewardship in the developing world. I'm thinking of the analogy of the landline of telephones and how they skipped that completely and went to mobile phones. What opportunities are there for them to skip coal and other types of power and just go straight directly to an efficient power supply, given that their current standards are very low and they may not need as many kilowatt hours?
It's a very good question. The opportunities are truly enormous, both on the side of leapfrogging, as this is called technologically, in terms of energy efficiency, in terms of understanding how to implement energy efficiency to go to scale, not just the technologies, but how to go to scale rapidly with policies that will get the energy efficiency into the hands of the consumers. To give an example, we all know that or most of us have heard about the US refrigerator story, where the refrigerators in 1973 would be using 1,800 kilowatt hours. An average US refrigerator would be using 1,800 kilowatt hours per year, and now it uses 450 kilowatt hours per year. I'm talking about the new model, and we think that we can certainly get to about half of even that number with known technologies, and that's on the cards. Now, if you buy a refrigerator factory for India using outdated refrigerator technologies, you then start producing refrigerators that are outdated, and those refrigerators get embedded in the Indian consumer market with lifetimes of 30 years each. Instead, if you switch to the state-of-the-art factory, you suddenly have an enormous baggage that you get rid of. Otherwise, you would be carrying a legacy of poor refrigerators that get embedded in the economy. So there are multiple investments that you could make in high efficiency, whether it's lighting, whether it's electronic ballast, whether it's refrigerators or appliances or vehicles or transportation, not just communication, where efficiency could start to come up to speed very rapidly and not have the legacy problem that often old societies are stuck with. Same goes for starting with photovoltaics or wind power, so you can leapfrog. So opportunities truly are very, very large.
I could jump in there. You know, I'll say something which Ashok said to me once about this, and he didn't just say, so I'll jump in. You know, definitely the cell phone is a good example that it being implemented in the developing world very in a kind of leapfrog way happened because in that case the capital investment units were smaller, and so it could be implemented in a practical sense, and so it could start well and it could deploy and grow, and then as it grew it could become more strong. And of course the power of having that individual ability to communicate is just unbelievable. It transforms people's lives in such a dramatic way. So that's held forth, and I think it is a terrific example. The thing that I think one has to be a little bit cautious of is, we would like, how do I put it this way? The people in the developing world, many of them, really poverty-stricken and want to find some way to raise their standard of living. And that's a life force that's unstoppable, okay? They want to do that. And so they're going to take to hand the technology which gets them a better life. So in the cell phone case, it worked. The new technology and where they wanted to go were perfectly coincident. There are going to be examples in the energy space that don't work out quite so neatly. In other words, what comes to hand most easily may not be the cleanest technology. And it's not going to be such a simple thing to say, oh, well, we would prefer that you spend a more expensive and complex route. And, what's going to happen is they're going to take what's available to hand. And that's why I think, to some degree, this laboratory could spend some time seriously having people think hard about what is likely to be the path by which energy is being adopted there, and what are some technology solutions which could be adopted to hand more easily than the ones which one might first think of and which could turn out to be more damaging to the environment. So there's a very complicated set of issues there.
Questions?
I'd like to differ a little bit with the thought of energy independence when we live on an Earth of ecological interdependence. And to follow on that theme, it strikes me that having a concerted effort, this is following the question about communication with the rest of the world, a concerted effort to meld behavioral change with the kinds of technological opportunities that might be envisioned in a way that makes that both decrease in the intensity of our activity with respect to energy and improvement in the overall quality of life, a package that people are readily able to grasp and feel encouraged by, so they'll adopt it. And I don't know how to do that, but that strikes me as the direction that we need to go. We need to make a future that is improved rather than constrained. And thanks.
It's a form of realpolitik. I mean, you have to deal with the situation as you have it now and try to make some progress without just imagining you're going to jump directly to an ideal world.
I think this is an example of the perfect being the enemy of the good. Otherwise, we wouldn't have talked about natural gas at all. But it's possible that that's a step in the right direction. Other questions?
So one thing that I see as encouraging is that people are now starting to intervene in land use with the goal of reducing fossil energy intensity. So this is biofuels, and with the goal of reducing greenhouse gas emissions. This is payments for reduced emissions from deforestation, forest degradation. I'm hoping that the three of you can talk a little bit about what role you see the lab playing in providing science support for this sort of land use management.
You want to talk about the soils project?
Land use.
Maybe you could give the microphone to Margaret Torn, who's sitting over here in the middle. Can you pass the microphone through on the...
You thought you could just sit and escape?
Yeah, see, I could answer this question, but I might not know what I'm talking about.
No, thanks, Avery. It's a great question, which is how can we also, in this way, combine the benefits of carbon sequestration or maintaining carbon in the ground and forests in the tropics. So the lab is doing some work that's related to that now, and we actually do want to do more. That was your question, right? Like, what could be the role in the lab? So we're currently mainly working on the soil carbon cycle, and one of the big unknowns in how much carbon is transferred with deforestation is what happens to the carbon stored in the soil. And then I'm going to point to Jeff Chambers, who's behind me, who's just joined us, who's a tropical forest ecologist, and Alan is working with him and doing a lot more in estimating what is the carbon that's stored in forests, what else may be happening to it, how do we use remote sensing to get at other forms of mortality of the forest, for example. And then forests do many, many things besides storing carbon. They also transpire water, which affects the atmosphere. They affect other aspects of climate. And we're trying, that's one of the things that's going on in the lab, is trying to put together forests in a bigger picture of climate and land use. And the other piece that we're putting into that is biofuels. But you probably knew most of that, so maybe it's good to have you guys answer that question.
So to answer it just on sort of another level, what we have that's maybe unique is an incredible capability in biology and also ecology at the lab and the various physical biosciences and earth sciences division and in life sciences division. We have the JGI also to help us understand how plants and other organisms work. And we have the other aspects of earth science and environmental science and some of the other divisions. And so we do have an opportunity to do something unique here with the combination of our bioscience and geoscience and environmental science capabilities.
I think the answer was adequate. I just want to add to my answer to your question about what can we do. And I completely missed on the ultra short-term thing that we can do in terms of global climate change. That is so short-term that it was shocking for me to look at the numbers. It turns out that we manage a significant non-trivial fraction of the Earth's surface as human-engineered surfaces. For example, the amount of roads in the United States add up to about 1% of US land area. Okay, that's the human-engineered surface. I'm not even counting rooftops. Okay? So if you were to think of changing the albedo of the rooftops and the human-engineered surfaces from, say, dark brown or dark gray to light-colored surfaces, is something entirely doable because you're already dealing only with engineered surfaces. And then what you have is reflection of visible spectrum sunlight back out through the carbon dioxide out to the outer space, because you are no longer trying to emit that energy back out as long wave infrared. It's coming back as either visible light or short wave infrared. That means the CO2 is quite transparent to it. It goes back out much like it came in with some scattering losses. Paul Burdell, correct me if I'm wrong, but the numbers that I recall is 100 square meter rooftop going from an albedo of 0.2 to 0.8, which is kind of dark gray to dirty white, is equivalent to taking 10 tons of CO2 off from the atmosphere permanently. Okay, so and Paul is saying this is the correct number in terms of independent estimates by two different groups, at least within 50% error, because there are uncertainties on all the calculations that I'm talking about. So if you were to paint all human engineered surfaces on the surface of the planet to a dirty white, the calculations are you are effectively dirty white because it gets dusted. You paint them white, but they get dirty, so I'm calling them dirty white. Okay, and you whitewash them once a year. Effectively, you take off 30 gigatons of CO2 on that order, and there is uncertainty around it, but effectively you are delaying global warming by 1 year of emissions, effectively, right? 30 gigatons. So that's something that you can effectively do just short of white paint and some brushes and people going around doing this. So this is something that is so ultra short term. You don't have to wait even 10 years to do it.
So I can actually speak with some authority on this subject because I have a home that has a white roof.
Hey.
And it's hard to do before and after tests to know exactly what the impact is, and I have no way of measuring tons of carbon. It has the additional benefit that my neighbor no longer talks to me. So if you're really looking for that double bottom line, white roofs are definitely the way to go. Next question.
Great presentations. Thank you to all. I guess my question is how you see the relationship of the National Laboratory in future with cities, particularly given that cities are going to house an increasing proportion of our population, focal points of consumption, and also a relatively weak political entity.
So that's a very good question. In my division, because of the applied nature of the research that we do, we have begun to connect over the past many years, and now that has accelerated very strongly, that trend of connecting actually with city governments to begin to work with them. So we work with, and the lab itself works with the East Bay Green Corridor, and they have come to your office and they connect with this because they see this as a way to grow green jobs in the East Bay Green Corridor cities. We work with the cities of San Jose and of the Silicon Valley as a way to help them get their carbon footprint down, because San Jose, the city of San Jose, for example, has a commitment to reduce their carbon footprint by 50% by a certain date, and they would like us to help them figure out how to do this. So there are multiple ways in which we can do this, but much better, the strongest way in which we can connect is locally, something right within our region. And we definitely have strong connections. And that's really important to us. And it's also important to the lab's policy now. You will see in the top 5 initiatives that Paul has highlighted many times that our work with the local community is very important.
Yeah, I mean, I would say, you know, it's interesting. It's almost like a kind of the fractal-like political dysfunction, right? On the global scale, we've got this problem where the national governments can't really quite all agree on how we would deal with problems like these. It's also true at the local scale, right? And it's probably even true inside your household. So, you know, there's a kind of these things are and possibly even, you know, depending on how many cells you occupy. So, you know, these problems are there. But I will say that in the Bay Area, there is a very active movement among all the local governments to try to have much more coordination. And Mayor Bates here in Berkeley has been extremely active with the Green Corridor, but these things actually extend all across the entire Bay Area, and the local governments are, you know, they do have some pre-existing things which they do with respect to air quality and things of that type. But increasingly, they're looking, for example, at trying to have uniform permitting for solar installation. Because one of the big problems that a solar installer faces is that every place they want to go and install their solar panel, they have to follow different rules for how to get the permits. And so it ends up being, you know, more than half of the cost, substantially more than half of the cost of the solar installation for a typical home is actually having to do, nothing to do with the solar cells itself. It's everything to do with getting permits and things of that type. So the governments here are working hard to try to talk with each other and develop some common policies and approaches to these things. And I do think that it is a fact that if we had a more regional approach in the Bay Area, there are a lot of things that could be done that would be much more sensible. And so, you know, there is a movement afoot among the local governments to try to do things like that. And I think every chance that we get to encourage the political figures in our system around us to take those kinds of steps, they'll be responsive to them. Yeah.
We are going to take a few more questions. We have a hard stop at 4:30. That's in 10 minutes. So, additional questions.
So my question is about solar. It's more related to the engineered surface comment and albedo. Now, I have heard that if 1/4 of all the engineered surfaces in the U.S. were covered with photovoltaics of current efficiency, that would give us more electric power than we would need. And so I was just kind of, you know, wondering what calculations you're aware of and any comments, because you didn't talk much about solar power and photovoltaics. You know, there was a lot of reference to natural gas and stuff. So I was wondering if you can comment a little bit about that.
Let's see. I think the answer is if you took, and I remember this from the artificial photosynthesis stuff, but it works just fine for the solar. If you took 60 million acres at 5% power efficiency, that would be more than equal to all of our energy use. And that turns out to be about 1/4 of the agricultural land, and certainly it's substantially less than all the roads and roofs, it turns out. So yes, you're absolutely right that there's plenty. I mean, you know, our problem in the United States is not the combination of sun and land. There's plenty of it if we chose to employ it. The question is, how would we actually, you know, implement that in some kind of practical way? Right now, the Department of Energy has announced just recently its so-called Sunshot. And the goal of the Sunshot project is to bring the cost of solar down to $1 per watt installed, fully installed for solar. At which point, it would actually be cheaper than the energy that, you know, you get by digging stuff out of the ground and burning it. It would be substantially cheaper than the energy that you're presently getting from PG&E. If we got to that, you know, $1 a watt, it would be really very impressive. It's unclear whether we can get to that, but the prices have dropped a lot, and they're probably in the neighborhood of $3.50 a watt, actually, right now, today, for solar, at which point it is practical to implement it on some scales. Certainly, this year, there will be 16 gigawatts of solar installed globally, and if you think of that as about $4 a watt, you know, that's actually as big as the disk drive industry. So, you know, solar industry is really growing. It's getting implemented more and more. There are things the U.S. could do to implement it. And certainly there's no question that if we did implement it at a significant scale, it could supply a very large fraction of our energy. It's possible to do that, no question.
We have time for a couple more questions.
Oh, great. I'm just wondering if you guys can speak to a shrinking budget or uncertainty when it comes to the lab and the budget and trying to solve these big picture, long-term thinking.
Sorry, we're out of time.
Well, I mentioned to you that I spent a lot of time in D.C. this past few months, and there's a reason. In the end, the budget this year turned out to be flat. And we were joking earlier saying flat is the new up. If we hold our budgets flat for the next couple of years, we'll probably be pretty lucky and pretty happy, and there's a chance that we could do that. We had a lot of growth recently. There's a lot of new projects here at the laboratory, and there will still be a number of competitions in the next couple of years, because even in times when the budgets are going down, new projects are created one way or another. and we can compete for those. So even if the overall budget's going down, we can have some opportunities ourselves here for some new projects to occur. So, and you know, to your point about how do we think about such long-term things when it looks like the budget's about to come and crash on us, you know, these, to my mind, what we need to do is have some really important goals for this laboratory that inspire people and that people respond to and want to really work on. And we'll work the funding, you know, over time. We'll get there. Yeah.
A couple more questions.
Here. I have a question on the carbon utilization. Many people believe the geoengineering like CCS is just an interim solution for climate change. So how you can do that effectively at the same time address the cost risks associated with geoengineering, and what's your scientist perspective on carbon utilization?
This is yours, Don. Did you want to try to, what was your interpretation of the question?
The question is trade-offs, I would paraphrase, trade-offs between carbon capture and storage and carbon utilization.
Okay. So I think the answer to that is carbon utilization could potentially be useful and important, but in terms of addressing the problem at the scale that it exists, that's probably going to be about 10% of the solution if it works really well. So in the end, you're still going to, so this would be a combination of, well, I think the idea that's out there now and being acted upon is using carbon for sort of building materials, cement and aggregate and that sort of thing. And there is a very large amount of building material used every year, so it's possible that that could cut into the carbon storage a little bit. But again, I think it's at the 5% level, and that's if it really is taken to the maximum. So I think you can't get around from having to store carbon somewhere geologically or oceanographically.
One more question.
Yes, hi. This isn't the first panel I've attended on this subject. And I think what is astonishing about this one is that it really is very optimistic, your assessment of things. But if you go, say, to the mid-continent, Missouri, Oklahoma, Texas, to one of these panels, you get a very different take. There's a lot of skepticism about whether or not there's climate change going on at all. It's believed that there is all a vast conspiracy, that those of us who believe that there is climate change are a bunch of socialists and un-American, and they just don't believe it because they don't want to believe it. So my question is, what will be the cost of carbon sequestration? And is that cost going to be, so high that after a while we're going to get a lot of pushback from people saying, look, this just isn't worth it. I don't want to have all the cost of getting rid of this carbon. It may actually end up becoming more of a political problem after a while if the cost of sequestration is too high. And is there a way that we could bring that cost down?
I'll answer that question, or try to. I'm sort of well aware that there's plenty of people who are skeptical about climate change, and there's different levels of skepticism too about, it may change, but it may not be as big an impact as some people say. With regard to carbon sequestration, I think my view, and from my experience now, I would say that the resistance to it is overestimated. That, in fact, most of this stuff would be pretty much invisible to the average user of electrical energy. Some decision would be made somewhere, and this carbon would be stored somewhere. There would be about as much impact on the population as there is with oil drilling now, or with locating coal-fired power plants. So we put up with that, and those have a lot of negative impacts. You wouldn't be looking at anything worse than that. In fact, it would be substantially benign in comparison to the impacts of having oil derricks and coal-fired power plants around. So I don't really think that that's likely to stop it. I think what's not there is any incentive for the industry to get into it now. And about the only place it's going to be done in the near future is this one demonstration power plant in the U.S. Called FutureGen, which is going to be put in Illinois. And that's because the government's going to pay for a substantial chunk of it. I think if they were doing a bit more of that and providing some incentives for power companies to get into this earlier, they would probably be doing it. They're certainly getting poised. The petroleum companies, I think, are learning all they can about what they're going to need to know in order to do this and presumably make money doing it. So I think it's not that far away from being ready to go. And there are some startup companies out there actually buying land and getting prepared to sell it as a service.
Can I add a couple of points? Between carbon capture and carbon sequestration, the two stages. One is to capture the CO2, second is to put it in the ground. 80% of the cost is in the capture part. 20% is the sequestration part. So the capture part is where the trick is in figuring out how to capture it at a lower cost. Berkeley has an engineering grant, a large engineering research, frontier research center, to figure out how can we do better, lower cost capture of CO2 using computational chemistry and so on. So that's what LBL is working with campus on. And there may be breakthroughs in that area. So that is one direction to think about. The second one to think about is as zero carbon electricity begins to get blended into the grid, the price of electricity will rise, but it is not going to be a step change for anybody. Right? So you begin to blend it in, and depending on what's politically acceptable, what the consequences are, to what extent people want to fight climate change and go carbon neutral, the price will rise, sure enough. But it's not like day and night, this 8 cents per kilowatt hour increase that we talked about.
I just want to jump in very briefly. You also raised the concern about people not believing the science of climate change. And look, there's no doubt that there's a broad set of topics on which there are, there's areas like evolution or other areas where there are just very strong, situations in society where some people don't accept the solutions that have come, the conclusions that the scientific community has come to. And I think that the science of the carbon cycle is increasingly strongly established, to my mind, having studied it the best that I can. It's really, it's a very, very complete and strong case. So I think it's up to us as a science community to be engaged everywhere we can. Each one of you, and it's part of our interaction with the community. As you know, I have listed that as one of the top 5 strategic directions for the laboratory, is for it to become deeply engaged with the community. And that doesn't mean just the local community, it means everywhere. And I think we have to be out there trying to explain how science works, what we do, and what the conclusions of this area of science are everywhere that we can. And over time, because that science actually does turn out to be really what it is, I think it's going to, that case will emerge. Yeah.
Before we close, I'd like to just offer the observation that you are all very lucky people. I started with the comment, you are what you worry about, so worry about something big. And I think, frankly, all of us are fortunate to be part of an endeavor. We may be a small part of that endeavor, but nonetheless part of an endeavor that touches the future. Some of my students are graduating next week and going off to work at Zynga, Facebook, well, whatever. That's nice. But some of them are working special role that the lab has in terms of advancing science and also advancing the public discourse, particularly on the subject of climate change, makes us very fortunate people to be part of an endeavor that really matters tremendously. I'd like to say thank you to our panelists, too, who have, for an hour and a half, been here to field questions that they had no idea what was coming.